Hello and welcome to the second video of section 3.4 on calculating limits at infinity. In the first video of this section, we made note of the result. For any positive rational r, the limit as x approaches either positive or negative infinity, if it exists, of 1 over x to the r is 0. To determine the limit at infinity of a rational function, we multiply by 1 over x to the m in the numerator and the denominator, where m is the degree of the polynomial in the denominator. To find the limit as x approaches infinity of the rational function f, we multiply by 1 over x cubed in the numerator and the denominator. We distribute 1 over x cubed throughout the numerator and the denominator, and the expression circled in red approaches 0 as x approaches infinity. Therefore, the limit of the rational function f is 1/2. This technique can be extended beyond rational functions to include roots. But before we work an example, it should be noted that the square root of x squared is not x, at least not at all values of x. Otherwise, the square root of -1 squared would be -1, when in fact the square root of -1 squared is +1. Note that the absolute value of -1 is +1. The equation which we are looking for is that the square root of x squared is the absolute value of x. This observation will be critical in finding the horizontal asymptotes of the function f. To find the horizontal asymptotes, we must find the limit as x approaches positive and negative infinity. We begin with positive infinity. Multiply the numerator and denominator by 1 over x cubed, the degree of the polynomial in the denominator. We can distribute through the denominator by 1 over x cubed, and with our observation that the square root of x squared is the absolute value of x, and the fact that x is approaching infinity, for our purposes here, the square root of x squared is equal to x. Keep in mind that the square root function is multiplicative, that is, that the square root of a times the square root of b is equal to the square root of a times b, which will tell us that the square root of x to the 6th is equal to x cubed. Therefore, the numerator of our expression can be rewritten, and 1 over x to the 6th can be distributed through the interior of the square root. The expressions in red approach 0 as x approaches infinity, so the limit as x approaches infinity of f of x is 3. Therefore, we found the first horizontal asymptote, y equals 3. Keep in mind there may be a second asymptote. We have to take the limit of f as x approaches negative infinity. The limit as x approaches negative infinity follows the same steps as the first limit, until we assumed that the square root of x squared was equal to x. We were able to do that because x was approaching positive infinity. Here, x is approaching negative infinity. So the square root of x squared is equal to the absolute value of x, and when x is negative, the absolute value of x is negative x. Therefore, the square root of x to the 6th is equal to negative x cubed. And multiplying the negative onto the other side, now the numerator of our expression appears very similar to the numerator as x approaches positive infinity, however it now is negative. We can distribute 1 over x to the 6th into the square root. The red expressions approach 0 as x approaches infinity. Therefore, the limit as x approaches negative infinity of the function is -3. Therefore, the function has two horizontal asymptotes, one at y equals 3 and another at y equals -3. In section 1.6, we obtained the limit laws for addition and multiplication. The limit of a sum can be calculated as the sum of a limit, provided that each limit exists. The same holds true for multiplication and subtraction. Keep in mind, however, that limits which are equal to infinity or negative infinity actually do not exist. Though they don't exist, in certain cases the limit of the sum of two functions can be calculated for limits which are infinite. Suppose that the limit of f as x approaches a is positive infinity, and the limit of g as x approaches a is positive infinity. This means that both functions have unboundedly large y values as x approaches a. The limit of the sum of f and g can be described as positive infinity. If two functions have larger and larger y values as x approaches a, then their sum will also have larger and larger y values as x approaches a. The limit of the sum of negative f and negative g can be described as negative infinity. Negative f and negative g have larger and larger negative y values as x approaches a. Therefore, their sum will have larger and larger negative y values as x approaches a. The limit of the difference of f and g, however, is not able to be determined. Take, for instance, the function x squared minus 1. As x goes to infinity, x squared and x squared minus 1 both go to infinity. However, x squared minus x squared is 0, and you're left with positive 1, and the limit as x goes to infinity of 1 is 1. We can change this example, replacing the value 1 with the constant c for any c. And we see that the limit of the difference of functions whose limit is positive infinity can be any value we choose. Therefore, it is not able to be determined. Very informally, when dealing with infinite limits, it is safe to assume that infinity plus infinity is infinity, negative infinity minus negative infinity is negative infinity, and negative infinity minus infinity is unknown. For similar reasons, using multiplication, infinity times infinity is infinity, which means that the limit of f times g is equal to infinity as x approaches a, when the limit of f and the limit of g as x approaches a is infinity. We also have that infinity times negative infinity is negative infinity, and negative infinity times negative infinity is infinity. The forms infinity times 0, infinity over infinity, and 0 over 0 join with infinity minus infinity in being unknown. These are called indeterminate forms because it cannot be determined with this information what the limit is. Take, for example, the function x squared minus x to the fifth. As x approaches infinity, both x squared and x to the fifth approach infinity. This leads us to the form infinity minus infinity, which is indeterminate. Factoring the expression leads us to the product of two functions, x squared, which approaches infinity as x approaches infinity, and 1 minus x cubed, which approaches negative infinity as x approaches infinity. We now have the form infinity times negative infinity, which we can determine, and is described as negative infinity. The function x squared minus x to the fifth does not have a horizontal asymptote for the positive x-axis because the limit as x approaches infinity is not finite, it's negative infinity. This tells us that the function's y value becomes unboundedly negative as x approaches infinity. This should line up well with your understanding of the end behavior of polynomials.